Hello, I am Pranavin Raj from Department of CSE AML. Today I am going to discuss about body-centered cube, crystal structure and its engineering applications. What is body-centered cubic? Body-centered cubic is a fundamental crystal structure where atoms are positioned at the eight corners of a cube with one additional atom at the center. This structure is widely observed in metallic materials and is critical to understanding material properties and engineering applications. The body-centered cubic BCC structure is a common crystal lattice arrangement in which atoms are positioned at each corner of a cube and one atom is located at the center of the cube. Cubic unit cell with 8 atoms at corners and 1 at the center. Total of 2 atoms per unit cell, which is 8 corners into 1 by 8 plus 1 center atom. One of the three primary metallic crystal structures, BCC, FCC and HCP. BCC unit cell composition. In a BCC unit cell, there are 8 atoms at the corners and 1 atom at the center. Each corner atom is shared among 8 adjacent unit cells. So the contribution from corners is 8 into 1 by 8, which is equal to 1, and the center atom is entirely within the cell, giving a total of 2 atoms per unit cell. The coordination number is the number of nearest neighbors atoms for each atom in a BCC structure. And for the BCC, the coordination number is 8. Each atom is surrounded by 8 nearest neighbors. The atomic packing fraction. The atomic packing fraction measures the efficiency of space utilization is approximately 68% for BCC, making it less densely packed than face-centered cubic but more efficient than simple cubic. The lattice constant and the geometry. Lattice constant, edge length of the cube, which is denoted by A, is related to the atomic radius R by the formula A equal to 4R by root 3. Atoms touch along the body diagonal of the cube, not along the edges. The lattice constant A equal to 4R by root 3, where R is atomic radius. The key BCC crystallographic parameters, the essential metrics defining BCC geometry and atomic packing. Atomic packing fraction for BCC is 68%. It is always denoted in percentage. Fraction of unit cell volume occupied by atoms versus 74% for FCC. The void space, percentage void space in BCC is 32% of a unit cell, which is the void space is the empty space in a unit cell. In BCC, the void space is 32%. It is very higher than the FCC, by 26%. Atoms touch along body diagonal 1 direction. Atoms at opposite corners and center touch. Space group LM 1M 3M. Body centered cubic space group. Bravais lattice type. It is a cubic with body centering. Atoms touch along the body diagonal of the cube, not along the edges. Examples and properties. The common metals with BCC structure at room temperature include iron Fe, chromium, tungsten, molybdenum, potassium and barium. BCC metals typically exhibit high strength, toughness and ductility due to their atomic arrangement. BCC structures have more interstitial space compared to FCC, which influences diffusion and alloying behavior. The octahedral interstitial sites, 6 per unit cell, larger, can accommodate solute atoms. Tetrahedral interstitial sites, 12 sites per unit cell, smaller than octahedral. Interstitial solubility. tetrahedral sites larger in BCC, affecting allying behavior, defect engineering, vacancies, and interstitials play major roles in diffusion and mechanical properties. Features atoms per unit cell in BCC 2. The coordination number of BCC is 8. The atomic packing fraction of BCC is 68%. The lattice constant A equal to 4R by root 3. There is some examples of BCC are iron, chromium, and barium. This structure is fundamental in material science and metallurgy for understanding the physical and mechanical properties of many engineering metals. Body-centered cubic. Body-centered cubic versus face-centered cubic structures differ significantly in their mechanical properties due to differences in atomic packing, slip systems, and defective behavior, ductility, and slip systems. In atoms per unit cell in BCR 2, in FCC is 4 and HCP is 6. The coordination number in BCC is 8, in FCC is 12, and HCP is 12. Atomic packing factor in BCC 68%, FCC is 74%. Slip systems, BCC has fewer slip planes, making it harder and more brittle than FCC, more ductile. The temperature behavior, BCC is stable at low temperature and FCC and HTP are more stable at high temperature. Ductile to brittle transition. BCC metals exhibit a ductile to brittle transition temperature, meaning they become brittle below a certain temperature due to insufficient thermal energy to activate all slip systems. FCC metals do not have a DBTT and remain ductile even at very low temperatures, making them preferable for cryogenic applications. Their strength and density. FCC metals are usually more dense and stable at high temperatures compared to BCC metals, though exceptions exist. Example, tungsten in BCC but very dense. BCC metals tend to be stronger at room temperature but less ductile than FCC metals. These differences make FCC metals better for application requiring high ductility and toughness, while BCC metals are chosen for strength and hardness at room temperature. Common BCC metals and elements: alkali metals like lithium, sodium, potassium, transition metals like chromium, vanadium, molybdenum, tungsten, and niobium. The iron phase, alpha iron, at temperatures below 912 degrees Celsius reverts to FCC at higher temperature. Barium, among the few alkaline earth metals with BCC structure. Industrial importance, iron is the most significant BCC metal in engineering and in construction. Mechanical properties of BCC metal. The strength and hardness. Generally harder and less malleable than FCC metals due to fewer slip systems. Conductivity lower at low temperature, increases significantly with temperature. Ductile to brittle transition. BCC metals show sharp transition, critical in structural design. High melting points, strong bonding between nearest and next nearest neighbors. Shock resistance, excellent for high strength applications under sudden loading. Thermal and physical properties of BCC. Unique characteristics influencing engineering application. Thermal conductivity varies widely. Electrical conductivity moderate, excellent in tungsten and molybdenum. Magnetic properties: alpha iron is ferromagnetic, essential for electrical steel applications. Thermal expansion, different coefficients across BCC metals affect design constants. Next, nearest neighbor bonding, nearly as strong as nearest neighbor bonding, affecting stability. Engineering applications, construction and civil engineering, high strength steel for bridges, buildings, skyscrapers, excellent toughness and fatigue resistance. Automotive industry, engine components, crank shafts, suspension system require BCC steel for strength and impact resistance. Structural steel, I beams, H columns, pressure vessels exploit BCC strength to weight ratio. Tool and die manufacturing, tungsten and tungsten alloys for high hardness cutting tools. Aerospace and defense, BCC titanium alloys, chromium vanadium for crafting landing gears. Engine turbine discs, structural components, excellent strength to weight and fatigue resistance. Electrical applications, tungsten filaments in incandescent bulbs, molybdenum in power electronics and semiconductors. Mathematical relationship BCC, lattice constant, A equal 4R by root 3, body diagonal length, root 3 into A, atomic packing fraction, it is 0.68%, D spacing, D H scale, A by under root, H square plus K square for Miller LDSS. Current research and future directions. Engineering project implementation, analysis, study BCC lattice parameters, compute APF, verify crystallographic calculations in phase 2 modeling, create 3D crystal structure models, simulate atomic positions and bonding in phase 3 property prediction, calculate mechanical properties using density, atomic mass and coordinate number done. In phase 4 application design, select BCC materials for specific engineering application, analyze performance. Phase 5 optimization, propose alloy component, heat transfer, processing rules for doing properties. The key takeaways are BCC structure is fundamental to materials science and engineering. 68% APF and unique mechanical properties in BCC, ideal for high strength shock resistant application. Wide applications from construction steel to aerospace, titanium alloys and advanced high entropy alloys. Future research in HCS, nanotechnology and additive manufacturing promises revolutionary in based materials. Thank you.